totally no texting, no answering 20 questions in the lab. You're welcome to leave, but not in the top.
Thank you, Norm. Thank you guys for coming. So what I want to talk about today, and if you noticed I changed the title sort of last minute, but two recent conjectures in pattern avoidance. And so it's going to be in two parts. The first part is a conjecture of a whole bunch of people sort of under the title Dokos et al. And if you're not familiar, this was an RU with Bruce Sagan, okay, from a couple years ago. And basically they had a conjecture, and what I want to share with you today is a proof of that conjecture by creating a new statistic preserving bijection between two sort of well-known or old sets. Okay. And then in the second part, there's a conjecture that had been floating around since 2012 due to Eric Egge up at Carleton University, and basically the conjecture stated that there was a collection of pattern classes, and we'll get to this in a bit, that were all counted by the large Schroder numbers. And it was a bit surprising that this was actually the case, and so we'll go into exactly how this is. And the reason that I'm putting these both together in the same talk is that the techniques used here are going to be very similar to the techniques used here, okay? Albeit the statements of the problems seem very different. Okay. So part one. The statistic preserving bijection. All right. I think we haven't had a talk on pattern avoidance, so I want to go through the basic definitions sort of slowly so that we're all on board, and then we'll get into some of the details. So, as usual, Sn is going to denote for us the set of all permutations. And we're going to think of permutations as a word instead of as an algebraic object. And if we think of it as a word, this would be an example of a permutation of length 7. All right? And we're going to be able to represent it on a grid. And so to represent it on a grid, I'm going to think of it in Cartesian coordinates. And so, for example, the 7 will be in the first column, and it'll be up 7 units. Therefore, the 4 will be in the second column, and it'll be up 4 units. And then if we fill out the rest of them, we'll get something like this. Okay, so this will be our way to represent permutations. Okay. Well, since this talk is about, in particular, patterns within permutations, let's discuss what a pattern is. Right. So let's do this through an example. Okay. So I claim that pi, this pi here, contains the pattern 2, 4, 1, 3. And the reason it does is because you can find within it 4 x's whose order has the same relative order as 2, 4, 1, 3. So, for example, we have a 2, a 4, a 1, and a 3. They don't actually have to be the values 2, 4, 1, 3, but their relative ordering has to be the same. So this one is the smallest, this one's the largest, and these two are in the middle, just like 2, 4, 1, 3. So in this sense, we say pi contains this pattern. Likewise, we can then talk about avoidance, meaning it doesn't contain the pattern. So this example avoids the pattern 1, 2, 3. And the reason it does is because you cannot find 3 x's that are going in increasing order. Okay, I can find 2, like this one and this one, but there's no third one up here. Because that doesn't happen, we say it avoids 1, 2, 3. Okay, so this is the idea of pattern containment or avoidance that we'll be using. And just some notation, in general, for any sigma, we denote by avn of sigma. This is going to be the set of all permutations that have length n that avoid sigma. Okay? And in this sense, I'm going to call sigma my pattern. So going back to the other slide, 2, 4, 1, 3, or 1, 2, 3 would be thought of as a pattern. And then I have this. Right? And now we really come to the main definition of study. Should get there quite quickly, which is this idea of Wilf equivalence. So one way, the way I think about this is it says that sigma and tau are equally difficult to avoid. The number of permutations avoiding one is the same as the number avoiding the other. So they have equal difficulty in avoiding one as avoiding the other. So in that sense, they're the same. And so there's sort of a relationship between things that are the same, and so we'll write sigma is related to tau in this sense, to mean that they're Wilf equivalent. And now, as I think this is the first pattern sort of talk, this sort of classic result has to be mentioned. All patterns of length 3 are Wilf equivalent. And in fact, they're all counted by the Catalan numbers. So if you recognize this, it's just the Catalan numbers. And that obviously takes some work. You might think, well then shouldn't just all patterns of any length be Wilf equivalent? Like all patterns of length 4, they should all be Wilf equivalent. I mean, that would be sort of a good first guess, but indeed that's not true. Okay. If you actually just crunch out some
guess, because 2 for n equals 0, n equals 1, n equals 2, n equals 3.
n equals 3, right. So then, yes, you have momentum, but you fall off the cliff. What's that?
Reminds me of the quintic parts.
Yeah, it's
for 1, 2, 3, 4, and then just not 5.
And not 5, yeah. Well, this it's not even true for 4. And even at 4, there's things that are quite mysterious about these numbers. So if I explain this, so this is the pattern or class, and then these are the number of permutations avoiding each one for that respective pattern. And if you look, there's these 3 different possibilities. And if you go and run through all patterns of length 4, you'll find that for any one you choose, it'll fit in one of these classes. Okay? And in fact, that's a theorem. There are exactly 3 Wilf classes in S4, and these represent them. And these are the 3. So just for some familiarity with these, this first one here, 1, 4, 2, 3, is actually the one we'll be talking about today. All right. This next one is the one that contains the increasing permutation, 1, 2, 3, 4. And likewise, by sort of a triviality, it'll also contain the decreasing pattern, 4, 3, 2, 1. And then, as I said, when I referenced this, I said, well, there's automatically things we don't understand about these numbers. The very first thing is the last one, 1, 3, 2, 4. This is, we have generating functions for this one and this one, but we don't know a generating function for this. In fact, there's sort of a well-known bet currently of trying to see how many terms can be expanded.
And Brian had for a while had the record.
It had the record. Yeah. So it's up to 30 or something terms?
No, 36. 36 now.
36 now, okay. So we know 36 terms, but nothing after that. Whereas for the other 2, we basically know all the terms. Okay. So this here is a huge area of study, but that's not what I'm going to talk about today. So what I want to talk about is the very first class, the one with 1, 4, 2, 3. And as part of showing that there were 3 Wilf equivalence classes, one of the key results in that, this classic result that dates from 1994, is showing that 1, 4, 2, 3 and 2, 4, 1, 3 were the same. All right. That is, yeah.
Are the Wilf numbers, if you flip the permutation, are the equivalents those 1, 2, 3, 4's Wilf class the same as 4, 3, 2, 1's?
Yep. Yeah, it's just because if a permutation avoids 1,
then it has
then
to
flip it, and that new permutation avoids the reverse of the other.
Yeah, they did backwards.
Yeah, and then in fact you can do any action of the dihedral group, because we're thinking of these things as embedded in a square.
Mm-hmm.
If you take any action of the dihedral group, then if 2 permutations are related by that action, then they'll be Wilf equivalent.
This is called triple equivalence.
So those are the trivial ones.
This one is not triple.
Yeah. So this one you can't get that way. This one requires some work. And the idea here used something it's not used that much these days, is this idea of isomorphic generating trees. And it was, okay, well, the thing is, you can show that they're Wilf equivalent by showing that they have the same recurrence, but it doesn't give you a bijection. Generally, we want bijections. So this was a non-bijective proof. And so the new results is that we give the first bijective proof of this classic fact. and it will simultaneously resolve a conjecture of Dokos et al. That I mentioned in the beginning. Right? But in order to state what his conjecture is, we need a bunch of more definitions. Well, not that many. We need the idea of a permutation statistic, which is this slide. Okay. So what I want to do is give you some definitions so I can explain what Dokos is, what the conjecture is. We'll state the conjecture, and then we'll look at what the bijection does. So, okay, so let's consider this permutation. Here's one that's of length 8, and within the world of permutation statistics, we could spend all day listing out tons of them. I'm just going to give you the few that we need, okay? And you'll get a flavor for what they are if you haven't heard of them before. The first is the idea of descents. So a descent, the descents of this permutation are precisely the positions where the value in that position is greater than the value after it. So let me highlight that. So if you see, in this position, this value is bigger than what comes after it. In this one, that value is bigger than what comes after, and likewise. And in fact, those are the only 3 descents in this permutation.
The first one.
I'm sorry? Oh. Yeah. Oh, it's because I changed it. Yeah. Okay, anyways, and the first one. Yes. All right. So, and there should be one there as well. So those would be the only ones. Right. Those are the descents. And it sounds just like what the term is. The next thing we need is this idea of a right-to-left maxima. Okay, so right-to-left maxima, there's sort of a technical definition, but the idea is quite simple. So the right-to-left maxima are positions such that the values in those positions have nothing northeast of them. All right? So if I look at these guys, there's nothing northeast of all those. But if I pick something else, let's say I pick him, there's a whole bunch of stuff northeast of him, this guy, and that guy. So the right-to-left maxima are the position, are these guys that have nothing northeast of them. And this will be a key statistic that we'll be talking about. And one nice thing about the right-to-left maxima is if you draw this sort of border, you can sort of represent where the right-to-left maxima are because they'll be the x's in the corner. So it's sort of the border that outlines the right-to-left maxima. And we'll represent a lot of things schematically that way shortly. And then lastly, there's this idea of plus or minus bonds. And a plus or minus bond are objects that look like that. So this would be a plus bond. They're things that are consecutive in value and position. And if they form sort of a positive slope, it's plus. And if they form a negative slope, it's minus. So we have that. So those are our plus and minus bonds. Okay, so now I want to refine this idea of Wilf equivalence using statistics. So if we fix our favorite permutation statistic f, then we say any 2 patterns, sigma and tau, are f Wilf equivalent, provided there's a bijection from here to here that preserves the statistic. And another way to say that preserve the statistic is that the statistic is invariant under the application of theta. Another way to say this is in terms of generating functions. If I keep track of the statistic, so I let t be the variable that keeps track of my statistic, this will be the same as that. So there's a few different ways to think about this. But in the end, what you're just saying is that the number of things with the statistic, a set value on one side is the same as the number on the other side. So it's sort of equidistributed. And now we can state Dokos' conjecture. It says that the patterns 1423 and 2413 are major Wilf equivalent. And now I didn't actually tell you what the major statistic is, but the major of pi is just the sum of the descents. And we actually don't even need the major statistic because of the theorem. Okay? The major statistic is the sum of the descents, but actually I was able to prove in the theorem something significantly stronger. Okay? And what I'll show you, or at least give you some sense of, is that there's an explicit bijection between these two sets such that theta preserves the set of descents. So if you have descents in the first, second, and fifth spot, and here, then when it maps over, it'll have descents in the first, second, and fifth spot as well. It exactly preserves them. And so therefore the major index is just the sum of those things, so that's obviously preserved. Okay, but it does a lot more than that. All right? It also preserves left to right, right to left maxima. It preserves minus bonds, and it preserves the position of n and n minus 1. So what this is saying is, if you're not familiar with this stuff, what this is saying is that these two sets aren't just in bijection. They don't just have the same cardinality. Their structure as discrete objects is incredibly similar. And that was what was missed in 1994. Although they said, well, they have the same size, what was missed is that they have, more than that, they have the same structure. And so that's what this shows.
So in hindsight, is it really trivial once you know, see?
Well, yeah, I'll show you the bijection. You can tell me.
It's so much structure, you think.
Yeah, well, it now is
but
to
you
me,
don't understand, but
yeah.
you have it.
Exactly, yeah. I think
You know, to find it.
it's hard.
Genius. All the smart people.
Are those conditions, are those sufficient to say that there is like an explicit bijection?
No,
Oh.
no, you can't sort of you can't play that game. I wish you could, but there's no, if there was...
Would there be other conditions you could add onto that, at which point that does become true? Possibly. Like maybe there's like
I don't want to say no, but I don't know what they would be.
Okay.
It's not like if we had an algebraic operation here, some sort of algebraic thing, then you would say, well, it preserved the algebra of it, then maybe you could say something, but we don't, they're just sets.
Okay.
So, okay. And additionally, one nice thing that you would want of any bijection with this property is that if it's in the intersection, you would hope your bijection fixes it. And indeed, this bijection does do that. One thing to check is that, have I done anything new? Is theta actually different from Stankova's original result? And the answer is it is different. For example, if you check in Stankova's thing, it doesn't even have this property here. Okay, it doesn't fix things that are in the intersection, and it also doesn't preserve any of those
But
things.
you said Stankova did not have a bijection before.
Well, there's an implied bijection by the generating function, the generating trees give an implied bijection, and if you back that out, it doesn't end up being the same thing. Okay. Okay. So now I just want to sort of go through and show you what this bijection is. Okay. So let's look at the anatomy. So I have 1, 4, 2, 3s and 2, 4, 1, 3s. Right, so let's start with the 1, 4, 2, 3s, look at what they look like, then do the same thing for the 2, 4, 1, 3s and see how we can match them up. That's basically all I did. So here's the anatomy of a 1, 4, 2, 3. If these represent the right to left maxima, we said we can sort of draw that outline, then if you look at where you can place anything else, they can only be placed in these blue columns. And one reason you can see that is if I had something that was not in this decreasing columns in the blue spots, so if I had something represented by those red X's, if you look at the pattern they make a 1, 4, 2, 3 pattern. So I'm forced to have these blocks be in decreasing order just like this. So on the 1, 4, 2, 3 side, I have decreasing columns. We're going to just summarize this. And now on the 2, 4, 1, 3 side, right, let's see what's going to happen. I claim it looks like this. And now it's not at all clear like what is that, and you have to stare at this a little bit to figure out. But it has quite a nice property. It actually has increasing columns. And I put increasing in quotes because it's increasing from the perspective of a single right to left maxima. So if I'm standing here at this guy and I look southwest, then the columns I see will be decreasing. So this is one column, this is another column, and if there was a third, it would have to be down here. So from the perspective of a single right to left maxima, I have to have decreasing columns, or increasing columns.
So there exists one.
I'm sorry?
There exists one for which this is true. There exists one of these
One.
orders.
No, No, from every corner.
Every corner.
For every, look at from this corner, I don't have it highlighted, but if you look, everything he sees, everything that's southwest of it, the columns are increasing. This one and this one are increasing from his perspective. Okay. He doesn't know about those up there. And likewise, from this one, from his perspective, he sees this column, and then the last one is trivial. There's only one column. So it's true from every column. And the reason why is, again, if I had the columns, they were out of order, I would create one of my forbidden patterns. So for example, if I have these two red X's, I would get a 2, 4, 1, 3. So I have increasing columns and decreasing columns. So now all I want to do is take something that's increasing and make it decreasing. This is it. That's the idea. So how do we do that? Okay, well, so this observation actually, when I heard the conjecture, I made this observation fairly quickly. And this is not to brag. This is because that observation actually, once I was like, oh, you can do this and this is really pretty. Then it took me another 6 months to figure out how to make it all work. Okay, so I'm going to show you how it makes it work, but in the paper it's about like 10 pages of details. But I'll just give you sort of the picture of the idea. This was sort of the hard part. Okay, so let's look at a 1, 4, 2, 3. These are the decreasing columns. And I'm going to look at the rightmost column. All right, so it's going to look something like this. That's what it's going to look like. All right? And I want to decompose it into 2 pieces, and then apply induction on those 2 pieces, and then stitch them back together. So the first piece is going to be sort of everything to the left of this last column, and this guy. He's going to get shared by both pieces. And then the other part is going to be this right-hand column, and all these right-to-left maxima as well that go with it.
Could you repeat again the first part?
Yep. Okay, so Pi1, the stuff in green, is everything except this right column. Okay? Including this point. This guy is included. He's shared by both. And then Pi2 is the right column and these right to left maxima. So we have those 2 things. Okay, so that's going to be my decomposition. And if we look at it, once I sort of reduce them down and separate them, I'm going to get this picture. And one thing to note is that this guy and that one are shared. They were the same point. So I have increased by 1, sort of the number of x's that are there. But that's okay. So I have these things. Now by induction, so there's, like I said, there's a lot of details to make sure that the border cases work. But if you grant me those, by induction, these are smaller than the original. And so I can apply theta to both of them. Right? And let me do that again. So because theta, I can assume by induction that it preserves all my statistics, including the right to left maxima. So if I apply theta to these guys, nothing changes. The right to left maxima stay the same on both sides. The only thing that changes is the stuff in here, there didn't used to be a prime there. So they've magically changed somehow. It's gone from B to B prime. But the structure is the same. So it maintains the structure. So that's great. Now I just have to stitch these 2 things together. So that's what I'll do. So how do we do that? How do I put them back together so that I can recover the full map? All right. Well, let's take the first one. And notice this is after I've applied theta, because I have a prime. And I'll take the second one after I've applied theta. And now what I'll do, remember these 2 things were shared. I'll replace this x by this entire picture. So we'll inflate this x by this whole thing. So it's a standard inflation operation if you're familiar with it, but if you're not, it's just stick that picture in there. That's all it is. And if I do that, I get this picture. And if you notice, what happened is this little section came down. And this got stuck. So this used to be that big green X. But now it's no longer there. It's been replaced by that. And yeah, that's it. That's the bijection. So you can show from this, it's not too hard to show that like descents and all the properties are preserved. An interesting thing about the bijection is that, and this maybe gets sort of to your question, not only are those properties all preserved, but in order to show this is a bijection, I needed some of those properties to actually be preserved. So it wasn't just an afterthought that they were actually necessary to make this bijective. This would fail to be bijective if you didn't have some of those properties, but you do. So you do this iteratively, and it does whatever it does, but it goes like that.
So the preservation of the statistics came after the proof or before? You already knew conjecture before?
Good question. Some I found experimentally by looking at what else was preserved to try and figure it out. Some by just studying what I needed to be true, I was like, I wonder if this is true, and then I checked it, and it was a mishmash of both to get it all. Like I said, it was the idea of increasing, decreasing came quickly, but the details were the devil's in the details. So it truly was in this case. It lasted way too long. Okay, part two. Okay, so
Part two. So the big picture is beautiful and elegant, but
Yeah.
the details are difficult to say.
the details are details.
Yeah.
Yeah, I don't know. Are they? I mean,
So there's no way you can do it in a few lines.
no, I don't think you can. You can't to prove it's actually bijective. It's
Oh, but the statement of the bijection is easy.
so
So that was a complete statement of the bijection.
this isn't basically a complete statement of the
But
bijection.
that's to prove that everything works.
To prove that everything works is
Yeah.
difficult. But this is the bijection. You just keep doing this.
Yeah.
There's a few little small things you have to take into account. That I didn't mention, but this is basically the whole statement. Yeah.
Can you go back to the slide where you had the maxes and the descending, where you're showing that it has to be in this particular block because it can't be anywhere else? So I'm just curious, what if you consider like the bottom left bounding piece of the whole, and then you did an analysis on that? Does 2413 have any properties like that? Or?
I'm not sure I understand.
So you have the top left. You observe this interesting property for 1423, where if you define that top left piece,
Yeah.
or top right piece, yeah, those top rightmost elements, or northeast is the one.
Oh, these right to left
Yeah.
maxima? Yeah.
Yeah. Now I'm curious if you have I don't know, left or right maxima. Like if you do it backwards, so you consider the bottom.
Oh, the bottom. Oh,
And-
yeah. There's inherent symmetries in this where you could do it all from the bottom as well.
So like, is it possible that 2413 exhibits the same behavior from the bottom as 1423 from the top?
No, that doesn't happen. Yeah. No. They are really, because you're taking as sort of like, because you've taken these two pieces that used to be sort of outside each other. You know, the A primes were up here, the B's were down here, and you've now put the B's inside.
Yeah.
If you do this iteratively, it's really giving the sense that you've taken something and turned it inside out.
Okay.
So it really has a flavor of turning something, it's like a sock and you just turn it inside out. Okay, that's really sort of the idea behind this, is turning it inside out. So no, they really are different from the outside. The two outsides are different, but the inside of one is similar to the outside of the other.
Okay.
So that's it. Okay, part two. Okay, so the large Schroder numbers and permutation patterns. That's sort of the gist. Let me motivate this with these numbers. Okay, we're sort of going to switch gears, but it'll come back to similar pictures. So this might sort of seem random, but consider these two permutations, two patterns, and you look at all of the permutations that avoid that pair. They have to avoid one and the other. And you generate those numbers. And then you compare them. You see, if you just do this, okay, you might very quickly recognize 2, 6, 22, 90 and say, oh, I've seen that before, because it's the large Schroder numbers. And then you get to the length 6, and it's off by 1. Okay. This phenomena happens all over the place, where you look at, you pick some patterns, and for a while they are exactly enumerated by something well known, and then at one point they're off by exactly 1. All right. So this is indicative of stuff that happens often. And so the interesting thing might